and you can start at the end of this year, so in the new academic year in November, whether you pass the spring exam or the autumn exam, but if you'd like to attend the spring exam, the deadline is on Friday. Any questions from yesterday? Yes. Yes. No, sorry, it's not the variational free energy, it's the variational energy. We're going to combine them. So we're going to stack them on top of each other. So you can do one or the other, or you can do both. Yes, two methods. Yes. So one way to do inference in general is to use variational calculus under the mean field approximation. And another way is to use free energy, which amounts to the same, under the Laplace assumption. And then you combine these two tools, and then you get a very efficient algorithm. An algorithm with its limitations, an algorithm without guarantee that you will find a global optimum, but a very efficient one. Further questions? Okay, so I'll just, as a quick form of recap, write down the two main insights we had in the previous two lectures. The first is that if you do mean field approximation, then you get an optimal Q of theta I. This is our Q star of theta I, which is proportional to the exponential of the variational free energy. And the important quantity here is, of course, this. The variational energy is the expectation of the log joint under all the Q's that are not I. So we've averaged over all the other partitions. We're left with a function of only theta I. We exponentiate this function, and we get our optimal posterior. And now, additionally, we can impose constraints on our Q. We can take the exact variational energy, or we can take an approximation to it, and if we take quadratic approximation to it, when we exponentiate a quadratic function, we get a Gaussian. And that's effectively what we're going to do. Yes? No, we don't have that guarantee. No. We do this in order to get an efficient inference algorithm. And because I work in neuroscience, I always have one eye on the brain. We also want to find the mechanisms by which the brain does inference. So we need to have mechanisms that are efficient, quick, and are possible to implement by connecting neurons. And this is one candidate. And in what follows, I will show you the kinds of evidence that we have. There will be somewhat less on the blackboard today. We'll sort of go back to the style that we had in the first lecture, and I'll show you some results. I'll show you how we apply this, and then we'll dive back into these derivations and apply all of this that we've sort of done in a free-floating way without filling this with much content. So we've always had this log joint and said, well, this is just our log joint. What we're going to do later is we're going to take a very concrete model. We're going to fill this with content, and then we're going to do this whole procedure. We're going to calculate the variational energy. We're going to do a quadratic approximation to the variational energy. We're going to exponentiate that, and then we're going to get our Gaussian posteriors that we want. And we shall see how this works in inferring what is happening outside and how the environment we're navigating is changing. So that's the main challenge here. So this is the first thing that I wanted to recap. This together is mean field approximation. I should draw the line again here, right? Is this the right height for the line? Is it too high? Lower? The lower I can get, the happier I am. Too low? Up? And the second thing we had is the Laplace approximation. And what we found there is that F is, I'm going to write down F and F is the log joint at our expansion point mu plus 1/2 log determinant of the covariance plus half the number of dimensions we have times log 2 pi. The optimal value for the covariance we have found to be minus the Hessian, again evaluated at our expansion point. So this is the Laplace approximation. Yes? Ah, sorry, yes, I missed the inverse here. Right. It doesn't matter. So I could take the inverse here or here. Yes. So what we had was, if I'm not very mistaken, but it can happen that I'm very mistaken. Let's see if I am. We set this to 0. Am I wrong? So we take this to the other side. And then, well, this is the optimal one. So, okay, so this is, in general, we have the partial derivative of f is this, or it's proportional to this. Let me do this exactly. 1/2, exactly. So what we do is we set this to 0. We disregard the 1/2. We take this to the other side, and so on. Huh? That's where it comes from. Good. And this is basically it for the moment. We'll go back to the next batch of slides. I will again send this batch to the secretary, and she can spread them among you. This will be a new batch. And then, as I already said, we're going to take a concrete model, and in the slides I'm going to motivate why we're going to choose the particular model that we're going to fill in here, and then we're going to do this whole thing for that model. And we will get a very interesting kind of update equation that allows us to update our belief about a whole hierarchy of states that we have about the outside world, just on the basis of one new input. So we make a new observation, and this new observation leads to a cascade of adjustments to our beliefs about the state of the world. And what's more is we have evidence that the brain also does this cascade of updates. So, new batch of slides. So, what do you see here? Yes, exactly. You see a black circle here. Is the black circle there? Is there a black circle drawn there? Not actually. So you only have these white lines, but your brain constructs a black circle. So your brain is actively working to construct your perceptions. So here they wrote, and this is from a paper by the famous researcher R.L. Gregory. We may see a video of him a bit later. Illusory contours and regions of modified brightness seem to be postulates of near eclipsing objects. So it's as if the black circle was obscuring these white lines partly. It's as if this was one white line and there was a kind of black ring obscuring the black lines at a particular point. And what he also writes is, it seems that an essentially Bayesian strategy is responsible. How can we interpret that? What is Bayesian about this? Yes? Exactly, exactly. Exactly. So we have priors about the objects that we will encounter in the world. Our brain has these priors. It's a certain question, a difficult question, to decide whether these priors are hardwired, whether we're born with them, or whether we learn them through exploration of the world around us. But certainly by a certain age, we have a very strong and unavoidable preconception of what objects the world consists of, and we interpret all information that we receive in terms of these predictions. So it's not always just the predictions themselves, the input themselves, but it's always prediction that modifies the way we see objects. Now here, there are two ways to look at this. One is that there's this shape here, and this is in the shade, but has the same color as here. And the other is to see a different shape here, a black one. And depending on which way you're looking at this, does anybody not see the two ways you can look at this? Okay. Look at it for a bit longer and wait until it switches. Mostly when you have a picture that you can interpret in two ways, if you look at it for a while, then involuntarily, without your control, it switches to the other way to look at it. But there are individual differences in this. This switching rate differs between people. So this surface here can belong to an object that has another surface here, another surface here, a hidden one here, a hidden one underneath, and so on. You see that. But then you can also see a structure that has this as its face and continues down here. And depending on which of the two you're looking at, this same surface seems white in one case and black in the other. It makes no sense. You don't see the shadow? In the second, no, but it's not a shadow. It's the surface itself, right? It's a black surface in the second way to look at it. In the first way to look at it, it's a white surface in the shade. The second way to look at it, it's a black surface. So the point is that the exact same drawing, the exact same surface here on the screen can, in one way of looking at the picture, seem white or be interpreted as white, and in the other way of looking at it, be interpreted as black. And it's your brain that does that, because your brain has a concept of the object it's looking at. And depending on the concept of this object it's looking at, it sees this as white or as black, or it interprets it as white or as black. White in the shade or black in the light. So in this depth ambiguous figure, the gray rectangular region changes in brightness for most observers. I mean, even here they say not for all observers, but for most observers, according to whether the area is a probable shadow. The systematic brightness change with depth reversal is clearly centrally initiated and a downwards effect. So we talk a lot about bottom up and top down. And bottom up is where the input comes in, where our sensory observations are made that need to be processed in the light of top-down predictions. And this is where the hierarchical thing comes in. That's why we have hierarchical models, and we'll be speaking about hierarchical models in what follows, because we have this hierarchy of prediction from above and input from below. And then you don't just have one layer, you have a stack of layers where the lowest layer receives the input, transforms it in some way, depending on the prediction from the next higher level, and passes information upwards. Then the next layer is updated, and the next layer does two things. It passes information upwards to the third layer, but it also passes information downwards to the first layer. So the top-down information for the first layer comes from the second layer, for the second layer it comes from the third layer, and so on. And the first layer receives input from outside, passes information to the second layer, and the second layer passes information to the third layer. And in this way, in this hierarchical way, inference on the outside world is performed. Now, of course, there are other ways to do inference. But we're so interested in this for two reasons. Because two things converge on hierarchy. The first thing that converges on hierarchy is simple mathematical theory. So if you have a model, so yes? Yes? That is exactly the point of the hierarchy. That is exactly the point I'm going to make now. So we have layers that look like this. X1, X2, X3. Now this is how we organize a hierarchical model. So it's a hierarchical model. And to have a hierarchical model, we need to have a likelihood and a, so let's add y, our observation here. We need to have a likelihood and a prime. So the whole thing is a joint distribution of y, x1, x2, x3, like this. But now, y only depends on x1. x1 only depends on x2. x2 only depends on x3. So we can take this joint distribution and write it as a chain of conditional distributions. P of y given x1. This is a likelihood. Now, basically, what we need here is a prior on x1. But x1 itself depends on x2. So the prior is now a conditional distribution. So this, we can call this a conditional prior. on x1. And then the same happens to x2. Now we need a prior on x2. x2 given x3. And then with x3, we're finished. And this, of course, this equality holds because of the product rule of probability. And this is what we call a hierarchical model when we have a prior that is itself a conditional distribution on a higher level, and so on. That's what makes it hierarchical. Yes? That could be. Yes, you can have a more complex structure. You have a more complex structure than this. This is just basically the simplest possible example. And what we find, yes? Well, what we want to have in the end is the posterior. So the goal is to calculate the probability of x1, x2, and x3 given y. So that's what the brain does. And the way we can describe this is by doing updates of x1 based on y, x2 based on, and so on and so on. Yeah. What are, sorry? I acoustically don't understand you. Those are states of the world. So up to now, we had theta, and theta was just whatever we were performing inference on. Now, as I already mentioned at the start, we're going to distinguish two kinds of thetas. We're going to distinguish states of the world and parameters of the model. But you can think of x as a kind of theta. So states will have names like x, and parameters will have Greek letters like kappa and omega and yeah, stuff like that. And these states, when we look at models that evolve in time, or that model, models where the states can evolve in time, we will have, of course, inference about these states that changes from point to point. So if I look at my belief about x2 at one time point, that will be different from my belief about x2 at another time point. But if I have parameters in my model like omega and kappa, then omega and kappa are going to be constant across time. Yes? Yes. What could be an example? Yep. What does it mean physically speaking? Oh. Physically, I'm hard pressed to come up with a physical example. So, of course, if you have different physical bodies, it's difficult to construct a physical system where one body only influences this body and this body in turn is only influenced by that body. So it is mostly when doing conceptual inference, as we do it, where we have one thing influencing the other, but not the third thing. So, for instance, it's much easier to come up with examples from economics. So let's say this here is the economic output that we observe. And this here is the number of hours worked. And this here is the weather. So depending on weather, more or less numbers will be worked on building sites, and this will lead to more or less economic output in a given region, for instance. Stuff like that. So the way we conceptualize the world. So some stuff influences other stuff, but it doesn't influence other stuff. Yeah, exactly, yes. And the inference will always be uncertain. So we cannot do exact inference, and that's why we always have these posterior beliefs that these quantities are in a certain region. That's why they're inferred. These would be parameters, because it's a static thing. So we're saying we're going to do inference on the month of March. We will come to these models where we have time steps, where we go along in time. So the most models that economists do about, well, of course they have lots of time series models too. But if you, in this very simple example, it would be just parameters. Yes? The Ising model, yes. So the problem with the Ising model is that the influence goes in both directions. So you don't have a clear directed graph here. So this is technically called, but don't bother with learning this, but it's technically called a DAG, and a DAG is a directed acyclic graph. So directed means there's always a direction of influence from one node to the other. So this is also a DAG. This is a directed acyclic graph. And if I have this, it's still a directed acyclic graph, but if I have this, it's no longer acyclic because it has a cycle in here. And in things like causal inference and models of how the economy works, directed acyclic graphs are popular because they're more easily tractable than others. But in the Ising model, you would have. Yes? What means, sorry? So we want to know in what region was the number of hours worked. So if this is our hour dimension, then we want to have an estimate of the number of hours worked, estimated from the economic output. So that's what we want to, so if this is our x1, then what we would end up with is a posterior on x1. So an estimate of the number of hours worked with a certain uncertainty. Because we're always uncertain about the stuff we're inferring. Yes? Yes. So we're going to get approximate update rules. Yes. So we will have a posterior at every level. For every time point at every level, we will have a Gaussian like this. Because we're enforcing that using the Laplace approximation, or something close to the Laplace approximation, but cleverer. So that's the meaning of hierarchy. It's a model that you can write in this manner, where the prior has itself a prior, and that has a prior, and so on. It's a hierarchy of priors on priors on priors on priors. Yes? Where the X's are states, yes. The example is the HGF, the hierarchical Gaussian filter. And we will be dealing with this at length in what follows. Yeah. Yeah. Good. Then another nice visual example. What do you see here? Who doesn't see an object in this? An everyday thing that you can see every day if you walk through Trieste. Who doesn't? Raise your hand. Okay, okay. You are the interesting cases. Now those who I saw someone, or I heard someone shout out what it is. It's a dog. Now look again, those who didn't see it, whether you can see the dog. Otherwise, I'll show it to you. Here is the dog's head. Here's the hind leg. Here are the four legs. Do you see it now? Yeah, so there's also a tree, yeah. Yeah. But the main thing is the dog. Now, but the interesting point is this. Now that you see, so we have evidence in this room that not everybody saw the dog from the start. But now that you see it, try to unsee it. Try to go back to the state you were in before you saw the dog. You cannot unsee the dog. oh, okay. Well, that's an interesting. Okay. But the point is, you cannot prevent your brain from predicting this dog once you have the prediction in place. How am I sure? Well, it's an empirical fact. Now, I could recommend, or of course I would never recommend that, but I could name some drugs you could take, and then maybe it will work. Huh? Perhaps it would work to unsee it under certain drugs. But as long as your brain is healthy and in its usual state, which I assume to be not on drugs, it will not be able to unsee this. Okay, top-down processing reveals the Dalmatian dog because you have an idea. Your brain knows what a dog is. It has a concept of a dog. And it can very flexibly rotate that dog and recognize it as a dog from any kind of angle or size that you look at it. It's one of the amazing things about our visual system. Yes.
There are many explanations of the inference of the code. For example, you can look at the correct of the neural network, which given the input that you think has the same space and goes correct like that.
Yes.
Which doesn't seem to I don't agree with biological classes or that there is a mechanical error there. What makes it there to other alternatives?
So what you said, okay, is a deep network that I would argue effectively does Bayesian inference. So that wouldn't be a different explanation. And you also have, I mean, perhaps you're aware of this Google Deep Dream, where you know, Google scours the internet for images, all kinds of images. And of course, the internet is full of animal pictures because people love to upload pictures of their pets onto the internet. The internet is full of them. So if you train a network on the pictures that are out there on the internet, you get a network that loves to predict animals. And now if you overweight the intermediate layers in that network, this network will see animals everywhere. You can show it an image of a tree and let the network interpret that, and it'll put a dog's face into the tree. So wherever the network finds an excuse to see an animal, it'll put an animal. So basically, the networks you described work in exactly this way, that they have these top-down predictions. And the top-down prediction is, you know, I've looked at these millions, billions of images of animals, so I really expect to see animals everywhere. And this top-down expectation of seeing animals shows up if the weighting between these layers is out of whack and you overweight these intermediate layers that are obsessed with animals in some sense. So the alternatives you were speaking about, I don't exclude that there are alternatives, but in this setting, I don't see them. And we know very much about the visual system in the brain, for instance, and this is anatomically hierarchical. So it starts at the retina. The retina is it is actually part of your brain. It's the back of your eye. It's full of neurons that capture photons coming in. And the first layer of processing takes place right in the eye, at the back of the eye. So the retina itself predicts its input. It changes its activity depending on what it expects to happen, on what kinds of photons it expects to be hit with, what wavelengths will hit it, if anything will hit it, and so on. Then the next layer of processing is in the LGN, the lateral geniculate nucleus in the thalamus. This is in the center of the brain. Then the next layer of processing is in so-called primary visual cortex at the back of your brain. And then from there, it spreads out in two directions. There is the so-called dorsal pathway that goes to the top of your brain, and this processes the where aspect of what you're seeing. Where is it? Where is it moving? What is it doing? And the second pathway is the so-called ventral pathway, which goes down to the temporal lobes. And this is the what aspect that is being processed of what you're seeing. Is it an animal? Is it a tool? Is it a human face? Is it whatever? What is it? And this is all done hierarchically. You have primary visual cortex V1, you have secondary visual cortex V2, then you have V3, V4. and V5 or MT, as some people call it. So you have this hierarchical organization in the brain. So for these two reasons, first, the theoretical reason that these hierarchical models are very good at performing inference when we perform inference on anything, when we build an inference machine. And second, that this is also the solution that evolution came up with when it built the brain. This gives us an indication that hierarchical models are extremely powerful at doing inference. Yes? For basically for all brains. I don't know how far down you can go in the visual system of, certainly in all mammals, this is the case. I'm pretty sure in all vertebrates, and I don't know if a frog brain also has this hierarchical processing, but I would expect it, yes. Yeah.
I think that brain has functional components in a hierarchical model. But what evidence do you have that it's better communication?
Ah. Yes. So we have to keep apart Bayesian in a rough sense and Bayesian in the sense that it is optimal. So it is absolutely clear that the brain is not optimal. And basically the first example is already up there on the screen, and I'll explain this in a minute. So the brain makes mistakes. I can guarantee you your brain is making a mistake as it's looking at this picture. So the brain is only approximately Bayesian, but you know, it has to balance two demands. One of them is that it be quick and efficient. Our brain already uses up, if I remember correctly, about 20% of the energy we use. Our brain is expensive in a biological sense to our bodies. So it has to be quick and efficient and not consume too much energy. And on the other hand, it must make the best use possible of the information it receives. So it must do something close to Bayesian inference, but it cannot do exact Bayesian inference because that would be too expensive in terms of energy and time. So there's this trade-off. There has to be a compromise. Okay, now turning to the mistake your brain is making. What is this on the right? Well, obviously, it's a cast of a human face. It's just a plaster 3D cast of a human face. I'll tell you that, and that is true, and I think your brain probably processes that absolutely adequately. Now, on the left, what is that? It's also a face, absolutely, yes, yeah. It is? It looks a bit further to, it looks a bit up, yes, but I acoustically didn't. It looks fat, okay. Yeah, so this guy's been to the cafeteria here, and the other one's been, and the other one's been to the gym, yeah. Yes, it's true. The one on the right. Huh? Very, very symmetric, yeah. Okay, yeah. Now you're on the, no, in some very general way, you're on the right track. So there's something fishy about it. But in another sense, you're not on the right track because the thing that's fishy about it is totally different from all you've suggested. Yes? Exactly. So what you see here is the face on the right is in fact the hollow mold of the face on the left. Though hollow, the mold appears as a normal face. Texture and even stereoscopic counter-information are rejected to maintain this highly probable but incorrect hypothesis. And as with the dog that you cannot unsee, you can try to force yourself to see this as concave instead of convex. But it doesn't work. It doesn't work. So I'm going to need sound here. I hope this works. I'd like to show you a video here.
We've got this little example of a sort of optical illusion here. So if you photograph it in the right way, as you're about to see, the eye plays extraordinary tricks on you. So there it is Einstein.
Let me, ta-da, show. No, it's just the standard Apple.
Little example of a sort of.
I didn't change the background image. I'm sorry. I should put up one of my own. It's just the thing that the computer came with. I think it's California. How can I show you this video? It shows on my screen, and I'd really love to show you.
This little example of.
Help is at hand. Aha. Thank you very much.
Of a sort of optical illusion here. So if you photograph it in the right way, as you're about to see, the eye plays extraordinary tricks on you. So there it is Einstein. There he is in profile. Wow. And there's the inverted bit, but hello. Your eye tells you that's poking outwards, and yet it isn't. That's the inside bit. And your eye refuses to believe it until you get to that.
That's great.
Oh, you're twisting my melon, man.
Isn't that extraordinary?
Why does it do that?
Well, it does that because your brain is programmed to recognize human faces. And it's one of the first things babies do is look at faces. And you expect to see a face. And even though you know it isn't a real face, your brain fills in the...
I did it again.
It's an astonishing illusion.
Does this, Stephen, does it only work with Einstein? Would it work with another man?
It would work with any human being. It is really creepy. It's amazing, isn't it?
But it's done it. I can't believe it did the same trick twice.
I know, the point is...
Right, listen, we're not going to fall for it this time.
And yet...
Okay. No way. Gone 3 times on the run. Outside.
This is going to be inside, Lee.
Inside.
Inside.
How do you do it?
Wow.
How did he do it?
It's so clever, isn't it?
He's so clever.
It is literally, we literally filmed this. I mean, you can see, that's all it is.
This is a great trick. I might cut my head in half and scoop out my brain.
What a wonderful thing. It would make the most wonderful blancmange or something, wouldn't it?
Wouldn't it?
Are we going to bother with the rest of the show? Because I could happily just...
What should I
I mean, it's lovely chatting and everything, and I love what we do, but let's just...
You're hypnotised.
Have you got any others apart from Einstein?
No, I tell you what we can do. We can make the Queen happy or sad.
Oh.
We've got a £5 note. You can do this with your own £5 notes, but we'll give you the demonstration.
Okay.
There it is. You do a little fold.
They've replaced the £5 note. I don't know if it works with the new one. Okay. Let me just show you the second video. This is a video of Richard Gregory, who's now very old. He's the one who did these pictures of the dog and so on that I showed you. Just 2 minutes.
Here is a hollow mask. The point is that the nose is actually sticking in instead of out. Now, your brain is simply rejecting it as being hollow because all the faces you've ever seen all through your life have had their noses sticking out. This one's sticking in. That's so unlikely, you simply don't see it. You can't see it. You reject it as a possibility. The brain can't cope with something that's very, very unlikely. One of the most interesting things about this is that you're fooled by it, deluded by it, but at the same time you know that you're fooled by it. I mean, you can look at the mask, put your hand in it, touch it, and you know jolly well the thing is actually hollow, and yet you go on seeing it with the nose sticking out, although you know that it's sticking in. You've got two awarenesses going here. You've got an illusion, but your brain knows that you've got an illusion, and yet you can't do anything about it. But there's no question that we have prejudices, we have built-in judgments which are partly inherited, partly due to our parents, our teachers, our early experience. And as you go through life, you begin to realize that half the things in your head which you believe to be absolutely true are fuddy-duddy and simply wrong. And the problem is trying to update your brain. You're born with an old, out-of-date brain through evolution. You have to keep updating it all through your life. And it's jolly difficult to keep abreast of changes both in the world around one and in oneself.
Okay, I think this is a good moment to have a break. Let's meet back here at 1:15. Okay, please take your seats again. Please take your seats. Okay. No problem. So now, we're going to slowly approach these hierarchical models that we use to describe the updating of beliefs in the brain. And the first step will be to show that under certain conditions, and actually quite broad conditions, Bayesian inference can be reduced to mean updating. This will be important in what follows. It's another one of the building blocks we need that'll come together in the end to form one big whole. So, as a very simple example of updating in response to new information, this is the example I've been using a bit throughout these lectures. Imagine the following situation. You're on a boat, maybe just like here. You're lost in a storm and trying to get back to shore, but you've lost all your modern equipment. That's washed overboard. And the waves are going high, and you can only see a lighthouse on the horizon. When you're at the top of a wave and when you're down in the trough, you don't see it. Now, the shore is dangerous, mostly cliffs, so you need to get to shore at the right spot. And in order to do that, you need to determine your position, and all you can do is measure the angle between the north and the lighthouse. Now, you make a few observations while you're at the top of a wave, and those are your observations: 76, 73, 75, 72, and 77. Now, you're going to have to do your calculation. What are you going to base your calculation on? The mean, exactly. I heard the mean. The mean. That's 74.6. And now, I guarantee you this is not a trick question. How do you calculate the mean? I didn't understand that, but I understood this. You sum and you divide by the numbers of observations. Okay, fair enough. That's a way you can do it. So the usual way is to do this, huh? Now, this has the disadvantage that it requires you to remember all of your observations, and this can become inefficient, especially if you have lots and lots of observations. You don't want to have to clog your memory with all of these observations. So, since the measurements arrive sequentially, it would be convenient to update x bar sequentially as the xi come in without having to remember them, and it turns out this is possible. After some algebra, we see that you can just simply update your mean as you make a new observation. And as simple as this is, I want to go through it because the structure is important and it'll remind you of something. So we have our current mean, x bar n. We can set that to 0 when we start the algorithm. And now we make our new observation, x n plus 1. We subtract our previous mean from that. We weight this by 1 over n plus 1, where n is the number of previous observations. And we add it to the old mean. This gives us our new mean. So this is a certainly quite inelegant way to prove this. You can do it in fewer steps and more elegantly, but this is one way to do it. Now graphically, 76 is our first observation. It's also our first mean. Then 73. Now, of course, the mean moves to the middle, using our little equation there. And third observation is 75, and so on, and so on, and so on. And in the end, we have 74.6 as before. But there are only two things we need to remember, and that's the current mean. So this 76 enters here. This 74.5 enters here. And the second thing we have to remember is the number of previous observations. And I'd like to draw your attention to this. Here we have 1/2, 1/3, 1/4, 1/5. So this goes down and down and down and down. The weight on the difference between the observation and the previous mean gets smaller from observation to observation. It is simple to show, I won't show it here, but it is simple to show that this amounts to, this is the same as exponentially down-weighting observations as they come in. So that's actually, I'll have to modify that, but we'll come to that. We'll come to the exponential down-weighting. This was premature. Let's just worry about this at the moment. So the building blocks of the updates we've just seen are prediction, new input, and again we have this important quantity, the prediction error, and the weight on the prediction error, which we can call a learning rate. So, does this generalize to Bayesian inference? And is it a general pattern? Yes. Indeed, it turns out that in many cases, Bayesian inference can be based on parameters that are updated using precision-weighted prediction error. So, as a repetition, the updates in the simple Gaussian model. We already had this slide in the last batch of slides. So this is just, again, Gaussian prior, Gaussian likelihood gives you a Gaussian posterior. And we said that when the prior and the posterior have the same shape, they're both Gaussian, we say this is a conjugate prior. So, these are the update equations for the precision and for the mean. We saw that. Again, we have prediction, prediction error, and learning rate. How much we're learning here, the precision of the observation, and how much we already know the posterior precision. This is all repetition. And as we shall see, this pattern is not specific to the univariate Gaussian case, but it generalizes to Bayesian updates for all exponential families of likelihood distributions with conjugate primes. So now, let's take this apart. Here, we fill in the equation for the posterior precision. It's simply the prior precision plus the observation precision. Now, we reduce the fraction by pi epsilon, and we get this. 1 over pi theta over pi epsilon plus 1. Now, this is already quite reminiscent of the mean updating we had, where we had 1 over n plus 1 a few slides back, when we were just updating the mean of a time series of observations. We had, as our weight, here was the new observation, here was the previous mean, and then we had 1 over n plus 1. Now, n, of course, was a natural number. It was 0, 1, 2, 3, and so on. Here, this is a ratio of precisions. Precisions are always positive, so this is a positive number. And now, this is since this is as if n had been replaced by this little fraction here, which is positive, we're just going to call this fraction nu. And since n was the number of previous observations in the updating of the mean of a time series of observations, we can take this nu as a number of virtual previous observations. So we said in the Gaussian update that in the update to the mean, this learning rate was how much we're learning here related to how much we already know. And this means that the more we already know, the less we're going to update. And this is now captured by the nu we have here. The higher nu is, the lower the learning rate here. The higher our prior precision is, the higher nu is, the lower our learning rate. So nu tells us how many sort of virtual previous observations are contained in our prior. For example, let's say nu is 1. Now that means 1 over 2 gives you 1/2. So the posterior mean will be exactly halfway between the prior mean and the observation. So if nu equals 1, this means the prior and the observation have the same weight. Our posterior mean will be in the middle between the new observation, y, and the prior mean. So this will be here if nu equals 1. If nu is between 0 and 1/2, and 1, it'll be here, closer to the prior. Am I making no? Sorry. So it's the reverse. So it's if nu is greater than 1. So 1 less than nu, and so it's like this. Sorry, the? Yes, but it's a kind of virtual number of observations, so you can say we have fewer than 1 observations. We will give our prior the weight of, let's say, 1/2. Yes. So when we have no prior idea, yeah. Yeah, you can call it overlearning, yeah, in some sense, yes, yeah. When you give your observation too much weight, yes. One way you can always formulate this is to say we're doing unregularized inference because your prior regularizes your inference. And actually, I mean, a lot of classical statistical inference, t-tests and stuff like that, which happily you don't have to deal with very much in physics. T-tests and all these classical statistical methods, ANOVA and so on, they operate with flat priors, basically with priors that imply ignorance on the whole line where the inference is made. And this is a dangerous thing to do because you get overlearning. Exactly. Yeah. Okay. And as we already saw, we can do this for all families of exponential distribution if we choose the right conjugate prior. This one here. Then we get the posterior simply by updating our hyperprior psi in this manner. Our new psi is the old psi plus 1 over nu plus 1 times the prediction error. And here the prediction error is a transformation or a simplification of the observation x, which is called the sufficient statistic here. This is the sufficient statistic function of the data. So the data are put through this map called T, and then this is our new observation in sufficient statistic space. And this is where we have our prediction error, and the psi's are referred to as hyperpriors because they are the priors on the priors. So this is our prior here, the whole thing. And our prior is parameterized, so basically defined by the vector psi and the scalar nu. And the posterior has the exact same structure as the prior. So this is as the prior here. So this is a conjugate prior. All the changes is that psi is replaced with psi prime, and nu is replaced with nu plus 1. So psi appears here and here in the prior. This is replaced by psi prime here and here. And nu appears here and here, and this is replaced by nu plus 1 and nu plus 1 here. But this is the same structure, and this is the update equation for the psi, and it is a precision weighted prediction error. And it has this structure of mean updating. So all you need to do to perform Bayesian inference with exponential families of distributions, and this is this whole long list of distributions that you see 1 or 2 slides before. Here, yes. Oops. Computer is slower than what I'm typing. So all of these distributions, the beta distribution, the gamma, the binomial, the Bernoulli, the multinomial, the categorical, the Dirichlet, the Wishart, the Gaussian gamma, the log Gaussian, the multivariate Gaussian, the Poisson, the exponential distribution, and many others. With all of these distributions, you can perform Gaussian inference simply by tracking the mean of your sufficient statistics. For every new observation x, you calculate the sufficient statistics. You take this function t. And then you just track its mean, because that's all this means. You're tracking the mean of the sufficient statistic. That's all you need to do. Yes, yes. I'll give you examples very shortly. Yes? That is a good question. So the question was, I don't know if everybody heard it. It was, how do we know what kinds of distributions we should choose to perform our inference? The thing is, you don't know that beforehand. You have a hunch, you have your experience, you do it, and you compare the models you use. So you use their free energy. You calculate the free energy of your model containing these distributions, and you calculate your free energy of the model containing those distributions, and then you look at which model is more surprised by the data, and you choose the one that is least surprised by the data. Yes? We're trying to find that out. So, yeah. Trying to find that out.
Do you have any clue that, how the brain to use exponential model for doing this
So, yes, we do have clues about that. So, I mean, there are studies of how the visual system works at a very low level. But what we mostly do is we look at how high-level concepts are updated, beliefs about high-level concepts. And we tend to compare models in that domain. And we do find evidence that usually our best performing models are these hierarchical models that keep track of associations in the world. So when A happens, B tends to happen also. But they also keep track of how quickly these associations change. So you need these two elements. You need your brain keeps track of the changes in, call these contingencies. One thing and the other somehow belong together. And then the world changes and they don't belong together anymore. And you keep track of this, but you also keep track of how quickly these associations form and are dissolved again. When we apply these models, and then we always apply a range of models to the observations we make, these are usually the models with the most evidence. But, of course, the complexity of your modeling also depends on the richness of the data you have. If your data aren't very rich, then simpler models will describe them better than more complex models. However, if you have a very rich data set, that will support using more complex models that are more realistic. Well, maybe the richer the data, the simpler the model. Well, maybe we're using a different concept of rich here. Yes. So I simply meant rich in the sense of allowing for inference on a whole range of parameters. If you have a data set where you only have, I mean, sometimes we only have 10 observations, sometimes we have 60 observations, and sort of in that range between 10 and 60 observations, you're often only able to fit 2 or 3 or estimate 2 or 3 parameters. And you're not going to get a very interesting model with only 2 or 3 parameters. Or the more interesting models have more parameters, but you need a data set that is, in the sense of the word that I have been using it, rich enough to support, more parameters to be able to use an interesting model. So all you need to do is to track the sufficient statistics. Yes. Yes. The exponential family of distribution, because the exponential distribution is also something. Yes. Yeah. Yes. 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 Yes, by definition you can, because t is just a function. You know, it's a function, you can put the argument in and you get t. So there are 2 slightly different kinds of ways that sufficient statistic is used. So you can take a number of observations and you can say, oh, I'll calculate the sufficient statistics here. So basically the first moment, the second moment, so on. And here, sufficient statistic is simply the name of this function. It's a function of the data that just think of it as the name of the function t, sufficient statistic. If I only have 1 x, I can still calculate the sufficient statistic. Psi is the so-called hyperparameter. Psi parameterizes your prior here. So, for example, it's always the simplest example, the Gaussian. So here's the proof on the next slide. And now let's do some examples. The simplest example that we've been using, sufficient statistic for the univariate Gaussian model with unknown mean but known precision, so pi epsilon known. Our example from the beginning. The function t is identity. T of x is x. This means updating beliefs about the mean simply requires tracking the mean of observations. Very simple. Now, what's slightly more interesting is the univariate Gaussian model with unknown mean and known precision. So now the sufficient statistic of, this is still a scalar x here. So we're making an observation here somewhere on the real line. That's the real line. This is our observation. We can call this x1 in the sense of where x is a sequential index. Okay, this is our observation. And the sufficient statistic is 2-dimensional. It is x and the square of x. Because if we just make these observations, x1, x2, x3, x4, and we're trying to fit a Gaussian to this, that we think these observations were drawn from, we now don't have the precision of our observations given as we had in this case, where we only had to infer the mean. We have to estimate the precision of this distribution. And for this reason, we need a second sufficient statistic. So we need to track not just the mean of the observations themselves, but also the mean of the squares of the observations. And this amounts to the first and second moments by which a Gaussian distribution is fully characterized. But this is all we need to do. If we have a series of observations and we want to fit a Gaussian to this, we need to track the mean of the observations using our mean updating formula, and we need to track the mean of the squares of our observation also using the exact same mean updating formula. Mm-hmm. Yes, yes. Because that is the sufficient statistic that's unknown. Yeah. The other one is known. And this generalizes to the multivariate case, where X is now a vector observation. Simplest example is the plane. So X is now here, and here, and here, and here, and here, and here, and here, somewhere on the plane, and we're trying to find the multivariate Gaussian from which these observations came. And then we track the mean of our X and the mean of the out product of our X, which is a matrix. But it's still the exact same equation. Very simple. So if we have a Bernoulli model, that means our outcomes are either ones or zeros, like coin tossing, heads or tails, yes or no, black or white. Then, as we quickly talked about yesterday, then the outcomes are all here. You know, you can tally up, oh, I had 5 zeros and I had 3 ones. But our belief about the parameter governing this follows a beta distribution like this. So our prior is a beta, and our posterior is also a beta, just a more peaked beta. So maybe the prior will be symmetric, because at first, we have no. So our prior looks like this, maybe, or even flat. Or we have a priori reason to believe that the coin is fair, then our prior looks a bit like this. But then the data come in, and the posterior looks something like this. So these are beta distributions. But the likelihood distribution, so the name of the model comes from the likelihood. The likelihood is binary. It's either 0 or 1. And the probability for a 1 is somewhere on the scale here. Somewhere around 5/8 here. So what we need to track here is the mean of our observations. Again, T of X is unity. And the prior turns out to be a beta distribution corresponding to new pseudo-observations with mean psi. All we need to do to get the posterior is to update the mean as new observations come in. Now, imagine you have more than just 2 possible outcomes. You're rolling a die. You have 6 possible outcomes. Now that is called a categorical model. You have 6 categories of outcomes. And the way you code this is that each outcome is written as a 1 out of k vector. So for instance, if you roll your die and you get 3, you code this in this manner. And you take this vector x, and you just keep track of its mean. The prior and posterior here, just by using the exponential family definition, is called a Dirichlet distribution. Now, a Dirichlet distribution is a multidimensional generalization of a beta distribution. And all we need to do to update our Dirichlet from prior to posterior is keep track of the mean of this vector. Now, a beta model, there are also cases where the likelihood is beta. So we make an observation, but we know the observation will be bounded between 0 and 1. So our observation may be a proportion. So we look at different, I don't know, different hospitals, and we look at what is the proportion of patients that are under 40, something like that. And this proportion will be somewhere between 0 and 1. So this is a beta model. The outcome is on a continuous scale that is bounded on both sides. And here, again, we have a beta prior and a beta posterior. And to keep track of that, our sufficient statistic is the log of the observation and the log of 1 minus the observation. Those two quantities we have to track as we perform sequential inference. A gamma model. Now this is a distribution that looks like this. It is bounded below at 0, but unbounded towards infinity. There's a gamma distribution. Not to be confused with a gamma function. A gamma function is something else. The gamma distribution. In order to, so when we make an observation where the outcome is always positive, but on a continuous scale. A typical example for gamma distributed variable is a waiting time. If you wait for something to happen, so you stand by the roadside and you wait for the next yellow car to go by. Your outcomes will be gamma distributed. The exponential distribution is a special case of the gamma distribution. So in sum, we have dealt with beliefs about states that are binary. These were the Bernoulli models, where we had outcomes that were either black or white, yes or no. Categorical, multiple categories. Bounded on both sides. Then we had a beta model. bounded on one side gives us a gamma model, and unbounded Gaussian. And this covers a lot. Probably most states of the world that you might want to perform inference on belong to one of these categories. And with all of them, you can use this reduction of Bayesian inference to mean updating. All you need to know is how to update the means of your sufficient statistics. And that's simple. Very, very simple. So all Bayesian updates of such beliefs take the form of precision-weighted prediction error. And these prediction errors and their precision weights are easy to compute. And the prediction errors are simple functions of the input. So for a second, it looks like we've solved all of our problems. But, of course, there are limitations. So, first of all, there are examples of distributions that are not exponential families. I've already given it away here. Students T. Who is familiar with this? This is not, yeah, some of you, but it's not part of the, okay, let me make a remark about T distributions. These are just side remarks. It's not part of the core physics curriculum. So, side remark, like I made a few side remarks yesterday about the beta distribution. Just take this as a side remark. T distributions. So, out of those who are familiar with T distributions, is anyone familiar with their history? Yes. So that is one interesting thing. That is why it's called student's T. It's often called a student's T distribution. And student was just the name he chose when he published the paper because he worked for a private company. And as you said, his boss didn't allow him to publish under his own name. Do you know what company this was that he worked for? You don't know? Okay, because it's interesting. It was the Guinness Brewery. So Guinness was already, this was almost exactly 100 years ago in 1916. Guinness was already a very large brewery then, and they went about their brewing in a scientific way. So they took fields that they had, and they planted different sorts of barley in different patches on that land, and they looked how the barley grew and whether the beer became better or worse, depending on, you know, whether you used this kind of barley or whether you used that kind of barley, and so on. And often they had a small number of observations. And this guy who published under the name of Student, whose real name was William Seeley Gossett, worried about performing inference with very small samples. And in the course of this, when he tried to find out, to get a mathematical handle on what he could say about things that he had only observed a very few times, how he could do inference on the underlying parameters there, he found this T distribution. And basically, you get a T distribution when you average over a number of Gaussians with different variances. And what you get is a distribution that I'm going to first draw something that I think might look a bit like a Gaussian. This here, we're going to call this a Gaussian. Now the T distribution is higher than the Gaussian in the tails and slimmer here in the middle, more highly peaked, and then again fatter in the tails here. So these are two distributions of equal variance. T of equal variance. And of course, sort of to compensate for the variance you get out here in the T, you have to have a slimmer peak in the middle. And this is when you're uncertain about the variance of your Gaussian. And this is mostly the case when you have few observations. Then you are uncertain about the variance of the Gaussian you have been making these observations from. These T distributions are mostly relevant when uncertain about the variance of a Gaussian sampling distribution. And this is the case when the number of observations is less than 30, as a rule of thumb. So there's this joke that to statisticians, 30 is infinity. So if you have a number of observations that goes to infinity, you will get a perfect Gaussian in the end. But from a point where you have 30 observations, your predictive distribution will look a lot like a Gaussian. So it will be practically indistinguishable from a Gaussian. But if you have fewer observations, like Gossett had in his Bernoulli field, then you need a T distribution to perform inference. And this T distribution has a very complicated functional form. and is not an exponential family. Another remark on t-distributions. These higher tails here than the Gaussian are called fat tails. Tails here are fatter. And precisely because they have fat tails, these distributions are popular, but perhaps not popular enough in finance, where you try to estimate the risk of a particular investment strategy. If you base your risk calculation on a Gaussian, you will, experience shows, underestimate the probability of extreme events. Underestimate the probability of the market going down 10 or 20%. Underestimate the probability of a big bank going bust, as with Lehman Brothers. So many people in 2008 who had used Gaussians to model the probability of a big bank going bust were caught out when Lehman Brothers went bankrupt, and they would have had more appropriate risk models if they'd used t-distributions for such events. So when you model risky stuff, use a distribution with fat tails. I also mentioned the Cauchy distribution here, and the Cauchy distribution is simply the special case of t for degree of freedom equals 1. So what I haven't told you up to now is the t distribution also always has an index. So there's t1, t2, t3, and so on. And this basically corresponds to the number of observations it's based on. And when you get to t30, then you're approximately Gaussian. And t1 is called the Cauchy distribution. These are just side remarks, not basically part of the curriculum. So these distributions are popular because of their fat tails. However, fat tails can also be achieved with appropriate hierarchies of Gaussians. That's an important point. Hierarchies can almost always produce the effects that flat models lack and you're looking for. So instead of going for a t-distribution that's hard to deal with computationally and analytically, you can also go for a hierarchy of Gaussians. Yes? The rest of these lectures will be about this. So, yes, exactly. Yeah. So this will be explained. Now, a further kind of distributions that are not exponential families are found in mixture models. Now, what is a mixture model? It's a model that combines several Gaussians. So you have one Gaussian here and you have another Gaussian here. And together, they give you a distribution sort of like this. Huh? Badly drawn. You get the idea, huh? You get this bimodal, it's called, distribution because it has two peaks. You cannot write such a model as an exponential family. But again, you can use a hierarchy of Gaussians to produce an effect like this. So, we saw that in exponential families, we have this precision weighted prediction error updating. And we saw that this covered a very, very broad range of cases of inference that we might be interested in. But we also saw that it had limitations. Now the question is how to get around these limitations when we encounter them. And here's a little recipe, and I'll give you an example of applying this recipe, which will again be the hierarchical Gaussian filter. Formulate the problem hierarchically, and as we discussed at length, this means to imitate evolution. Because evolution also built a brain that is made up hierarchically. Separate the levels of the hierarchy using a mean field approximation as we learned yesterday. Derive update equations, and amazingly, at least in the case we're going to look at, these update equations will still, or again, have the structure of precision-weighted prediction errors. So we will retain, by applying this recipe here, this structure of belief updates that are precision-weighted prediction errors. And the example that we'll look into is the hierarchical Gaussian filter. And this will be the next topic, but before we go into that, let's have another break. Back here in a quarter of an hour, please.